Okay, now there will be sound. Yes, my bad. Sorry for those joining online or watching later. The initial part was without sound. Now there is sound. Okay, thanks, Stefan. So then the get item must be implemented. I will show you just a second what it means. Again, remember 2 underscores means the operator functions which you can override in Python. By the way, the same stuff you can do in C++ as well. There is the you can override the plus signs and so on. So here in this part there must be somewhere also that I need to override len function, which I don't find it now, but there must be. So the len function and the get item is the main ones which I need to override. And there is even cool stuff which I did not notice before, that you can do the add. So that means the plus sign from 2 datasets, and it will make a concat dataset of those. That's cool. I did not notice that before. Anyway, so I will just show you what it means. So the get item, here we implement get item and length, yeah? So if I do following stuff, so print here from 0 index or whatever index, right? The index 1 and so on. So it will call this function and execute this part. So this gives it the appearance of being an array, okay? So and then I also can do the len, and it will be this guy calling. So far clear, right? Yes, okay, so if something not clear, definitely interrupt, and that's why we're here. So that's part that. Then let's maybe start adding some breakpoints and exploring this stuff. So if I add here a breakpoint, so we are loading this from my server. Then it uses the pickle library. Pickle library. Remember we talked that you cannot just copy the contents from one pointer to another pointer, from one instance to another. There is the serialization procedure, and this is one of the serialization procedures called pickle inside the Python that allows to serialize it in binary format. It's sometimes a bit tricky, because if you start serializing actual classes, then if you use, for example, different version of the library, it will fail. But if I serialize something that is very simple, like just integers and floats, then it will work. So now, because pickle is not always the answer, definitely. So now if I debug this, let me see what we get there. Okay, cool. So we stop here. The dataset I think is the same as yesterday. Just quickly go over it again. So what we get here is self labels. Let's look at first self labels. So first one is brand, I guess, the Chevrolet, Honda, and so on. So let's see what is the let's see how many labels we have at all. Len self labels. By the way, if I add a breakpoint, you see that in the console it's super easy to debug here. So it's got four categorical items. I don't list here the, I guess the, I have it actually here. So the categorical items: brand, fuel. So the fuel is diesel or petrol. Transmission, automatic or manual. The seller type, personal, or the what was the other one? So dealership, the year of make, and the kilometers driven. So, okay. And before, so what we also do here, so this is actually the whole X structure, but we select out. So what this part means, can somebody explain?
From 0 to 4.
Mm-hmm.
You're selecting all the rows and the columns from 0 to 4, excluding 4.
Yeah, you're right. So exactly, the first part means include all of the rows, chick, and then if you imagine Excel, right, all of the rows, but that only include the from 0 till in 3 including, or 4 excluding the columns. And these are the ones listed here: brand, fuel, transmission, seller type. These are very specific because they are not scalar values, they are indexes. So we give the manual transmission index 0, the automatic transmission index 1. I cannot just feed model with string, this is automatic or you know, manual. I guess if you have like a pre-trained language model, you could do that, but that would be such an overkill, you know. it's always for these deep learning models to try to format data is as smart as possible, not to model, give the model that please understand the way how I spelled this stuff in my language and then encode it inside. So we don't do this. Okay, so that's that. Then the other part, so maybe somebody could explain a little bit this block of code just to understand if you understand it. Just look at it a little bit and think about it. So see that here the key is this. So we are selecting here something and doing something here. What we are doing there.
Standardize the data.
Okay, and from what kind of data actually? Yeah, so if I scroll a little bit down here, you see that year and kilometers, right? Yeah. So here we are skipping everything up till this part and just using those two columns and doing some stuff here. And you're saying standardizing, right?
We are
so
normalizing.
Why we need standardizing?
Because machine learning puts data in similar manner, and
yeah.
Cannot be from, I don't know, 80,000 kilometers to 200,000 kilometers, because it's two big difference.
Yeah, that would be, it'd not be great if we have huge values, right? The kilometers, 300,000 kilometers, I don't know, somebody sells that cars, maybe let's say 100,000 kilometers, but in Germany probably much less. We buy all of the German cars. So basically here the year and kilometers, very big difference, right? The year, so it's just four decimals, right? The four numbers, right? The kilometers, very large number. That's completely different scales. We need to make them in the same scale, make the neural network work easier. So again, that's one thing that I keep reminding is that it's many times a lot is about the data engineering just before training. So that is that. Then the prediction part, again, very interesting. So let me get to that part to see if this is actually what we need. So we are not predicting just one value, but we are predicting two values. We are predicting the number of owners. So this is either as the car one owner had or two owners or zero owners, and selling price. Again, standardizing to make them easier to learn for the model. And how we can get back the original value. What do you think? So if I have a model that predicts price for a car, and it will give me the price 0.5. Okay, what does it mean? Or minus 1.2. So how can I get back the real price? Because now I do the standardization, right?
Yeah. Okay.
Then also another thing which might be slipped away somewhere. So we train the model on dataset, right? But then we will run it on something that the model has not seen, right? That is kind of key, that the model is able to predict things even though it has not seen that sample any time. So, and then it shows me some value for the car price, which is nonsensical for human beings. So how to use this to restore the value?
We're using the same things we used when we're changing from kilometers to standardized data, but in reverse.
Yeah, reverse. So we use the equation to get inversely to get back the same value. So to use that equation, so what would be necessary is to save these guys. So we can even write it here. So so just not lose it, because if I don't add it to the self as a member variable, I will lose these y mean and y standard deviation, right? But if I store it in the class as a member variables, then I will not lose them, and I will be able to recover my real price when the model is trained, and also the number of owners. So that's good. By the way, the number of owners might be also smart to use it as classes, but forget. Let's keep it as it is right now. Okay, so I'm adding this also small change to the Jamboard. We'll have quite a few things to the Jamboard, so it'll be fun. Okay, so this is cool. Again, small question. So, is there any reason why we could not predict just price without the owners? Can we do that? Yeah.
Without the owners?
Yeah.
Yeah, of course.
Yeah, sure. It's well, like I just adding the two outputs for the model just because to show you that there is importance of how the matrices are structured, and that it doesn't mean that at the end there is always one just scalar value. It can be anything, you know. We can even predict and we come in like all sorts of properties and come out all sorts of properties, you know. So it's these models are not just you know, producing one value. So that's good. Okay, so far so good. Then what we do next is split into 80-20 train and test datasets. Why do we do that? Do you know? Yeah. Yeah.
So we obviously need a training data set so that our model can learn the underlying patterns of the data set and thereby make predictions. And then the training data set is what you've just mentioned. We want to test on, primarily we want to test on a data set the model has never seen before, so that it can generalize well relatively, because normally it's the case that your model tries to predict values it has never seen before, because there's just much more data out there the model has not seen as opposed to the data it has seen.
Yeah,
you can also test on the training data set.
Yeah, we did test on both, but the test is the guiding point, because what can happen is that if I create a large model, it can learn not the underlying kind of logic, but each sample themselves.
And
so
that's overfitting, and you can prevent it.
Yes, and then basically what happens, it learns every sample in trained dataset just because that combination means that, and then it gives something it never seen. It thinks like, okay, and I don't know that kind of information, so that's not what we want. Okay, so then we have the data loaders, which again previously with the Walters you implemented yourself, but in this case we can use the Torch based version. So let's add the Torch based version. So quite a few functions we can use from Torch directly, but hopefully if you had at least a little bit of time looking at how these functions work inside, it's kind of important to understand what you're doing, because like if you don't understand, it's super easy to mess up things. So here the data loader, again, so why do we need at all data loader? Why not just use each sample from the data set?
It would just use too much memory.
Sorry?
It would like use too much of memory.
You mean like if we will just load whole data set and try to train it once, right?
Yeah.
Okay, that's one explanation. Yeah, but in general, on what data loader does? What is the main function for the data loader? So we have data set where we can select by one sample, right?
Yeah.
And we have data loader.
We are like reading batches.
Batches, right? Yes, for the batches, right? And we train it by take together some batch of samples, do some update again. Okay, so cool. And then there is all sorts of formulations for that as well, but let's go step by step. So this is the data loader. So the first parameter is the data set train. The second parameter will be, okay, then we can just use maybe okay, batch size, we have the batch size, I think, yes, so the batch size, so this will be that. So then shuffle, so the shuffle means that I want to shuffle the indexes before drawing batches, and for training dataset that's very good. Again, these are small details, very super important. If we just not shuffle things, we will get really bad stuff, because especially like for example, if we have the dataset of cars being added to the dataset by the months, so winter months, summer months, so on. So model starts learning winter, goes in one direction, those summer goes in another, and where we stop, there we end, right? This is not what we want. So that's why the shuffle is good. So then drop last. This is an important part for the batch size. I hope we will have time to implement batch norm. So we already do one kind of normalization. I will just quickly implement this stuff and explain. Train. So I'm checking that modulus from batch size. If I try to divide the length of train by batch size and I get one sample, then I drop this stuff down. So this will be that. And then for the test data set, it's similar.
So it needs to be divisible without any rest.
So it needs to, so it can be divisible. It cannot, it might not divide, but then it should be at least 2, you know?
Why should it be at least 2?
Yeah, because, just a second. So, and here the false, so at least 2, because there is the thing called batch normalization. We will work with this, but just to understand now, when you do the standardization of the data set, remember make everything around 0, right? Like from -3 to 3 or something, like 3 sigma or something, sigma. So then the idea here is this, that if I have in the model somewhere in the middle some kind of normalization or standardization feature, right? I need to calculate the mean and standard deviation. If I have just one sample, I cannot calculate standard deviation from one sample, you know? So that
you should also not do it from like 2, so
yeah, that's,
maybe you should aim for a larger reminder.
That is valid point. Yeah, that is a valid point. I think technically you could do it from 2, but yeah, that is a valid point. We could maybe, let me think what we could do. It's just that there is one thing. So for example, the batch size, like if my my resources, hardware resources, allow me to put in like 256 batch size, and I'm just taking all the full batches, then I lose some information. But if the batches are small, then so let me see. Let's your idea is not too bad. So let's write it. So if the batch size, what is the batch size? 16. So that is not too bad idea. If the batch size is less than half, then we will drop it. So yeah, that is valid point, that standard deviation will be quite off just with 2 samples. So as you see, understanding details makes quite a difference here. So then the model itself, so this is again similar structure as before. The forward, the backward here is missing. We could implement backward as well. Then the torch NN module, everything that you see is always inherited from torch NN module. If it's not inherited from torch NN module, then there will be some issues which I will explain. So this will be the model. So we will implement model as well. Then the optimizer, we remember that guy. So what optimizer does? Yeah.
Yeah, as the name implies, it optimizes the model, but in detail.
Remember the code before. Maybe we should open the code before.
Yeah, but to be precise, it tries to optimize the weights. So that's the entire point of the training process. If there is a loss, so difference between the actual and the predicted value, the model measures it, and based upon the loss function, the stochastic gradient we've seen yesterday, the optimizer orients it.
So see the optimizer code here. So what does it does? What the code does? So this is the code from yesterday, right? So the first thing that you need to optimize these models. So you need, the reason is we want to find the weights, right? The weight matrices and the biases to make everything work great, right? To predict the correct car price at the end, right? And to do this, we need to change the weights because initially they are random, right? And then to do the change, we need the partial derivatives, gradients here, right? And then we multiply that by small step and move in the direction of the gradient, right? So that's the optimizer thing. The ways how to improve it would be also to take in account the speed of the movement to some direction, maybe create some momentum, do a little bit of random stuff there, so to try to make it smarter. There are smarter optimizers, but this is the simplest one. So again, you see that, and also there is the thing which hopefully Walter's mentioned, is that PyTorch by default, every time when I call backward pass, calculates the gradient value, gradia, but it not only calculates it, but adds to the previous value. Adds. If I call like backward to model backward like 3 times, it will be 3 times bigger gradient. So it's not resetting the gradients, it's just adding it. And this is the reason, because there will later on, I think on Tuesday, we'll look at the recurrent neural networks where there is like time series in time, and it's important to keep adding the gradients. And that's why there is the zero add, which nullifies all the gradients. It says that, well, let's calculate again, you know? So, and the other thing to notice is the parameters. Remember, we need to collect all of the learnable parameters because there is the inputs and other things which are not learnable. It would be very bad to start learning the actual inputs of the, so it will try to, you know, change, okay, this to get this price, we need to change this car, some stuff, and then later this is nonsensical model, you know? So we could theoretically also learn the inputs, by the way.
But is it different in TensorFlow? So is the loss always recalculated?
Do you mean the accumulation?
Yeah. So is it accumulated or not?
I don't remember. Need to check. Might be, might not be. I need to check them. So then the loss functions, and then the training epoch, right? So the first the epochs. Then we go through the first pointer to the data loader, the second pointer to the data loader. Then we put the eval mode. Then we put the train mode. So these parts, don't worry about them. They just say that we will accumulate gradients, we will not accumulate gradients. And then the bottom part is just that, there is nothing else there. So, but again, if somebody is worried, so we could write this code like much longer, you know, to see like variable, are we in the train, are we in the test, and so on. But if you can just use the basic knowledge of the programming, just use the list pointer of this guy, list pointer of that guy, check this is train or test, and make it work, you know. So we try to write the code short but readable. So that's that. Okay, so we're ready to start working properly on the code. I'm now looking at the tasks, so 4.2 tasks. So implement MSA loss and MSA, and I did not add actually the model itself as a task, so let's implement the same model as yesterday. So I will find where is the model structure. So just the same model implemented in PyTorch, and maybe with the different loss function if you want. So just a second, this will work today. So okay, transition. Okay, so here the Jamboard. Okay, so here is the model from the yesterday. And let's do this here in the PyTorch as well. Don't want to press the wrong button. Okay, so here's the model, and let's start writing it. So self, what is the layers? I guess torch, and then sequential. We will look also another type of structures that can be used here. The sequential is the dumbest kind of structure that can be used for creating a model, but this is kind of like a list or array where everything goes step by step. So if I call first function, it goes in the second function and so on. But as you will see on Monday, there is options to not do it like that. We can just calculate something on this side and then calculate something on this side and then combine them together, and then it's not so this is again one reason why yeah, no, but you can definitely do that also in those TensorFlow Keras stuff, but usually TensorFlow Keras is just like sequential models, not models that are like with the different paths combining, going back and so on. So we'll see. So there okay, so the model is consisting of two linear layers, sigmoid in between, and that's about it. So let's do it. So torch, and then linear. So this is the linear layer. A linear layer in features will be the, so let's initially, so we will have the 2 plus, we'll later change this, but let's try it first of all as it is. So two values which are the scalar values, kilometers driven, and what results the year of make, and then the 4 categorical values. So that's why 2 plus 4, but we will change this a little bit later. I leave it in that format. So then out features 16 as it was, torch and sigmoid. So sigmoid. So does sigmoid have learnable parameters? Yeah, so no, this is just like a dumb function that executes to every cell in the matrix. It doesn't have any learnable stuff there. So, but linear does have. Linear is basically linear is w dot c dot x plus b. Okay, so good. I will need some help here. So then, what is the in features here? Yes, 16, correct. What is the out features? Remember, we talked about dataset just before. So we're predicting price and the what was this, the other, like the number of owners, right? So 2, right? So we're predicting price and that, and they are standardized. Okay, good. So this is our genius model, really small. Nothing there, but we could make, so you already see we can make it much deeper, much more interesting as well, very easily. Okay, so this is good. Then the forward pass, again, very simple. So self layers forward. Again, here is very interesting thing that, just a second, I hope that might be that x is not what I need here. Okay, let's just use the 2 here because the x classes we will handle a little bit different, and so it will not go directly into model. So this will be first kind of interesting change. Okay, so just let's take the kilometers driven and years made. So those kilometers driven and years made goes into X, and the X classes goes everything else, all of the categories. And you can define these inputs as you want. It doesn't need to be like some specific format, except all of the inputs first dimension must be batch. So all inputs first dimension batch. I think that's about it for the model. You can very easily make it deeper. Again, I forgot to mention that here we can write backward pass as well. There is no backward, but backward. So we could do this, and so this would, the way how this would work then is, I don't know, something like I take the layer. You don't write it now this, but I'm just showing you. So you take the layer, get some kind of parameter, I don't know which one, and then add some grad here. So basically you can do this, but it's not necessary because the PyTorch as the differentiation as the derivatives tables are just tables, so we can automatically assign that this type of function have that kind of derivative, so it can derive these derivatives itself. So that's a good news. So you don't need to do derivatives in most cases. In some cases where the functions are not derivable, which is the case in sometimes, then you need to write the backward pass with some kind of hacky way to do the derivative. But otherwise you don't need it. It will do the grads themselves. So when I call the backward, it will go and find, for example, the linear here, there is the dot product. What is the derivative of this guy? I will do this, then apply the chain rule, add the grad to the value, and so on. And I don't know to do this myself. So that's why the TensorFlow, PyTorch, like very popular to do, because like you don't need also to do all the grads yourself, but at the same time you can do grads, and this is sometimes very important. And also important to understand how it works, otherwise it seems to be magical, but it's not magical. So this part. Okay, so this is the model. I'm dropping the model to the Jamboard. Let's move on. Then the optimizer missing here. Let's see what will be the optimizer. Torch, and you can play around with optimizers as well. Oh, sorry, is it torch and n? No, torch optim. So there's a lot of optimizers. By the way, RMS prop was invented by that Karpati, like he's Andrew NG student. Actually, I like his approach better than Andrew NG. So then the SGD, Adam is very popular, but SGD is the one which we implemented. So this is stochastic gradient descent, exactly the same stuff as yesterday. So then the first parameter is model dot parameters. Remember, we made this function as well to extract all of the learnable parameters from model. And in this case, this function is already given to us. And this works only because we are using member variables. Remember, member variables are those variables which are self dot something. And member variables which are inherited from torch NN. So if I go inside this function, by the way, this is a great way to explore all sorts of libraries. Just press Ctrl and go inside the functions and see. So it goes to the parameters and yields parameters, or returns the list of parameters. So, and this function again looks for learnable parameters in each of the named members. So and that's why it works. So this is this, and then the learning rate. I think it was what was the call? Okay, the learning rate, but do we have it? Yeah, so learning rate. So and that's about it. So the optimizer is ready. Again, very little work, a lot of output from just using PyTorch. So this is this. Then we are moving further away to the loss function. Okay, I will leave the loss function for you to probably. Oh no, we have Huber loss as well, so you will do that yourself. So the first one, the very simple torch. So the mean square error, right? Mean square error. We'll put the equation so we are not confused. I think it's quite simple, anyways. Okay, so I don't have it equation, but so torch mean. So the mean value of all of the difference between these guys, so y prim minus y and squared. Hopefully somebody already told you that in Python and also PyTorch overrides, so the square is this funny looking thing. So this means basically a squared, right? So if this a jig means a squared, right? So this is the Python way of telling this. Again, the main kind of thing to remember about loss functions, all loss functions must return just one scalar value. All loss functions must return just single scalar value for the whole batch. So we could calculate it for each sample, but then it's no use of batch. You know, like we need to calculate some kind of total kind of error of the whole batch to approximate the effect of the wrong weights for the whole batch. We don't want to calculate for each sample separately. That's why we need one value which is multiplied with all chain rule to all other derivatives down the road. So this is that. So and there is another one small thing which we, as you see, we implement ourselves the model and we implement ourselves the loss function, right? So these two blocks of things, it's very recommended to implement yourself, not to use ready-made stuff, because especially with the loss functions, it's very temptatious just to take, okay, let's torch loss or mean square error. The problem with that is that in many of these equations, if you go into documentation, they made it in different way than it is intuitively given. You know, I have seen it many times. People adding some kind of cross entropy loss and then wondering why my model doesn't work, because you don't understand what you're actually doing. You know, the equation. So you have like double by ex or something like 2 times exponent or something that doesn't make sense at all, just because the guys who made it intended to use it in a different way. If you made it yourself, you understand how to use. And these basic blocks like linear sigmoid, they are hopefully basic enough to understand. So, but as soon as everything becomes more advanced, it's kind of easy to make a mistake. Okay, and then the last part. So now we are here at data loader. Data loader. So this is actually the model execution. It's also not hard. So I hope I added to the Jamboard the stuff. Loss, yeah, okay, y prim. So this is the model, forward, x and x classes. And I will add the breakpoint and explain, because somebody might notice that we are not using anywhere the variables anymore, but we are actually using variables. The data loader is smart enough to convert NumPy values into torch float tensors. So, and float tensors are basically the same thing as variables. So they are containing the actual value and grad. Value and grad. All of these x's, y's, everything contains value and grad. They are not just matrices. They are like double matrices, you know. So we will look at that in a second. And also the learnable parameters are inherited from these, you know, the tensors. So that then the loss function. Forward, between, again, it's better to have the correct order. Hopefully it is. Yeah, y prime y, yes. And then finally adding the losses. So I'm adding this to the list for visualization. I want to see how well my model is doing, right? So what should happen with loss? What we want to get with loss? What kind of value one we want to get here? Closer to 0? Yeah, closer to 0, right. 0 is perfect. So it will go like initially it will high, go down, 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 and then it's called convergence when it stays the kind of about in some delta same. So that's what we want, yeah. So this is working. Then so we are missing one crucial step, actual learning, right? So if data loader equals data loader train. So we are right now in the cycle where we go over only training samples, not test samples. We calculate loss also for the test samples, but not learning from them. So here what we do is we call backward, and this is again one difference from what you did yesterday, is that we are calling the backward to actual tensors, to actual variable instances, not the models themselves. And I will explain just in a second. I will add a breakpoint and show you why this is. Because if I would implement this way in the NumPy, it will be very, very confusing, but it makes sense. So, and then optimizer step. So now we are stepping the optimizer, and then we zero grad. And that's it. This is ready. So I am adding this to the Jamboard. Now we have, I think, ready code for the training. I will add a breakpoint here, and we'll see if everything goes well so far. Okay, so we get there. By the way, this code is also added in Jamboard if somebody is not getting along. So, but I'm showing it here as well. So okay, what we get here is the loss tensor. So we can start looking at the final loss value even. So final loss value looks something like this. And the first things which we notice is that here is the, okay, maybe it's not, it's visible here. So the loss, this is our loss value. This is how bad is the model right now. And then there is a grad function pointer to the mean of backwards. And remember that mean square error, the first function is mean, right? So it remembers like a linked list what was the previous function I was calling, right? And that's why I can call backward to this guy, because it remembers always the grad fun. Each of these variables always have the grad fun, and so on. And then if you look here carefully, so loss data, maybe I can make it larger. Loss data. So we have the actual value here, and then we have loss grad, the gradient, except yeah, this guy doesn't have gradient. Just the weights have at the end gradient. So we can get to the gradients as well. So let's see, model parameters, for example, list. So this is, we can look at what is our parameters in model. So there are all of these weight matrices, right? So the first let's see, so this will be the data. So this will be the first bias, I think. Yeah, so 16 elements in a row. And then first bias grad is this thing, except it's nothing. Why it's nothing? Because I've not yet executed the backward pass, that's why it's nothing. So now if I press again, now I will have it. Yeah, so see? So before I was not yet over this step. If I do this step, now I have actually the gradient as well. So the gradient is given for us. It's calculated by this autograd function. Basically, as I said, it will not give you the best analytical derivative that you can do manually, but it will give you a derivative which gives mathematically correct results and which can be automated, which is much better than you don't need to sit at that equation like for 8 hours and then at the end find that there is a mistake. You know, it's better to have something which is not maybe the optimal speed, but at least it works perfect. You know, so this is how it works. And then the optimizer, and then we run it. And then what happens is the loss becomes smaller. So we already see quite cool results. So it is training and getting better results. So it's getting to closer to real values. And at some point, by the way, it might not happen here because we have very little, very small model. But remember I told that it can learn every sample by heart, right? Every sample, to know every sample individually. We have I think 8,000 samples, but the model is just 16 vectors, so it's very hard to remember all of the samples. So that's why it's not really overfitting. By the way, this is one of the reasons, one of the fundamental things. When you build models, if you use the least amount of parameters, it will also help to prevent the overfitting. It's kind of, but at the same time, if you have less parameters, you may not get the best results. So it's kind of always the struggle.
I'm getting narrow.
Okay, now yeah, right. So let's stop for a while here, and I will go over make sure everybody gets it working, and then we will move on. But before I go to you, I will just try to achieve the overfitting stuff. So I will just make it huge, maybe not huge, but much larger. Let's make it huge model. I'm not sure it will actually, still it will be large enough for that stupid dataset, but we'll see. So, okay, I'm adding now very large model. We'll see if I get the overfitting. We'll see. Maybe. It'll be great if we get. Okay, so.
Because I haven't defined the y mean, I've defined it up here, but I'm not sure if it's correct if I write the cell.
Yeah, but then you need also here self. See this? No,
yeah.
Here, no. See there? Where is my finger here?
I also need to write
yeah, exactly. Yeah, it's not here. There. Yeah. Great.
Every 10 epochs.
Yes.
To close the window and then it starts again. Then it's not so.
Yeah, I know. It's maybe you could if I have time, I will look also up. So this is kind of called scientific view in the PyTorch. Somebody know how you must be able to enable. I don't know how.
Because Wassos told me yesterday that this is the community version. So
in community version you can.
So on my own laptop, it's also with the scientific version.
Yeah, but I was I didn't know that they disabled this feature for community. This is kind of stupid, actually. Annoy you to get them paid, right? I will put you in this window all the time until you pay me, right? So, but you can see already this is quite cool. So this would be kind of overfitting that the test loss is getting higher than the trained loss. Yeah. Yeah, no worries, I will stop. So, yeah. So it says that I cannot do the dot product, the matrix multiplication between this and this is 16 by 2 and this is 16 by 16. you have the matrix multiplications only in the model here. So there's a 16, and the one thing which I changed is that I didn't use here 4, just because the other 4 guys are living in X classes, and we're not yet students. Okay, we're not yet resident. Yeah. Can I help you or something? Yeah. Okay. No, okay, the row class should be a union, yes. So we'll see. Okay, so this is kind of Python stuff because it will actually from any programming language, it will start executing code from data and read. Okay. So it executes this guy, then it compares these two, and then it divides it from that.
Okay.
So brackets. Yes, brackets after that and before
every time it's like every after the show,
but
you can like exchange it for I don't know if
and then I think we'll just remove the last bracket probably. It will work also. Try it again. Okay, you use the comma. See, this is not working.
Oh, yeah, huge.
Try it again. Oh, okay, great. Oh, now it's training. This is correct, but the way where it's coming from. Okay, this is from batch. The collate is the batch loader actually. Okay, so I think it's data set somewhere. Data set, please. So see, there is no right. Hold on. Well, you that's fine.
Nee, irgendwie nicht. Soll ich das schicken? Wenn du schon gefragt hast.
Hold on.
Das könnte weg. Peter, was hast du gemacht? Hast du irgendwas verändert?
Basically, it means something is not right with the I had a breakpoint in data. Get item. No? No. We have one line down. Oh. Just add here. Here, let's see. So, I don't know. Okay, but now we just set the last return also. And you this in the console copy there. We will see what you can but if you change all of this stuff just to okay, so this is very interesting.
Was hast du denn
Just says open
Ja, Fehler gewesen mit Y-Min, Y-Min und so weiter.
Wo war das jetzt Variable?
Ja, das, wenn man es speichern soll, dann ist das
just right.
Maybe that's right. So versions go back up.
Aber einmal habe ich schon vergessen gehabt. Weil das musste ja dann auch nachzustellen.
So it definitely get items.
Ja,
Okay, so try to
Das macht dann weil die Y sind die Ausgabewerte, die du speichern musst, und die X-Werte sind doch eigentlich gerade die nicht aus deinem
Yeah, I mean that's
that's aber du kannst ja nicht einfach auch wieder das Datenset holen.
Ja, nicht, wenn es geschnoppelt ist.
Wenn du da fragst. Ich finde die das Frage.
So I know.
Hast du den Code auch mitgeschickt?
Well, let's try that. 64 here. Again here. And the
Wollen wir mal sehen, ob
one,
Dresden exzellent zu nehmen ist.
Oh, it doesn't matter. The match with
Oder ob da nur viel heiße Luft in der
here 64 as well.
Yeah.
I did not notice that there is this guy. You're right again. Yeah, if somebody is finished, please help each other out as well because I'm trying to struggle with this stuff.
Ja.
So then,
Leider einfach weiter.
Oh, God, that's a lot of stress.
Warum läuft das beim Seminar nicht? So, das fing ja die
integer 64 or long. That's not really that. Maybe it works right now.
Okay, it's okay. Let's go to another.
Try to change it to long.
I like I just here and then
Not long, just long. Try again. If that doesn't work, I will show more in case. In case it doesn't work. Okay, so at least one of you have. So this is you see the overfitting situation. This is not classical overfitting because the data set is something is not too simple, but basically usually it starts getting up so this is not good, but I'm just showing you. So you want both lines to go down and not diverge. So but then I think one of you had this problem here. I think you're Mikola, right? Jarko. Okay, yeah. So you had a problem here. That somebody have a different PyTorch version, which don't understand how to change these guys into torch tensors for some reason. So to fix this, I will write it down. So but most of you this works anyway. So float tensor like this, and I'm casting the type from the numpy to this first of all, and then only returning. Normally, in almost all cases, PyTorch should understand this themselves, but it seems that some versions do not. So classes torch long tensor. It's actually good to know that something like this exists. Y torch float tensor. I will try to run it to see that it actually works.
I think you actually have to reinstall it, the libraries, for every new script you create.
Yeah, so it works. So like try to write it in this way. If it still doesn't work, then let me know. So if Jarko this still doesn't work, then let me know. So yeah, definitely, I'm coming. Yeah.
So also maybe a general question. So because you have to store the y values themselves on an instance, but you didn't store the
No, it's should store also. Only later when I want to use this model, it would be nice to have them. But like for this example, if I just train it with what I have, I want to see what is the real value and don't use it for production, then I don't need it.
So my consideration was to because maybe you have the input as
No,
data.
you're right. What's your name again? Felix. Yeah, Felix is saying that should we also store the x values here for standard deviation, and that is a good observation. That if I want to use this model on production, then I also need to store these values, because then later I will not know how to use them anymore, because I trained it on this specific type of data set. Then I need to use the same mean and standard deviation later. I cannot just calculate it from scratch again. It works, right? So yeah, if there's some issues, you can write it in that way. So is there any other problems? Can I help out? Did you help each other? Right? Yeah. There is just one thing which I want to go over before the lunch, which is kind of very important for the next part as well. So right now we are missing one thing here. We are missing here the X classes. We are ignoring the car brand, we are ignoring the automatic manual and so on. Not good, you know. The Mercedes and Lada doesn't cost the same way, right? So we should give model information about the brands as well. So one like kind of easy way would be just to, as I did in the beginning, just to say here of +4, right? Let me reduce this ridiculous model, make it smaller. But then this is not good as well, because if I just feed in the indexes of the car brands, we will have a serious problem. I will show you in a second. So the problem arises here. I will show the Jamboard just a second. So the problem, if I want to just feed the model with indexes, right? So I'll try to do my drawings. Hopefully they will not be too terrible. So imagine that we have this x inputs on x-axis, y on the y-axis. So this is the input for layer, layer, so the or X, right? And this is the output from layer, right? And in between layers, what do we have in between layers, right? The non-linearities, right? So you remember did you try ReLU as well, right? Yesterday.
Yeah, we tried.
Yeah, so the ReLU, and then there is sigmoids, right? Let's try to use
We
maybe.
didn't. It was our homework to implement it.
Okay, did somebody try to do this, right?
Yeah.
Okay, so but ReLU looks like that, right? So that everything that is on the left side, on the minus side, becomes 0. Everything that is on the right side becomes the same value, right? So it's not, if it would be a linear function, it would look like that. And then it doesn't, like, basically the kind of funny trick is that if I use a linear, so what it means linear is that I have this linear stuff here, I have some input, I get some value out here, right? So this is the input, this is input, this is output, right? So whoops. So here's the input, here's the output, here's the input. And if I add these lines, so one linear layer, another linear layer, another, the last linear layer will rule everything, right? Because so it doesn't matter how many linear layers I put, it doesn't totally matter because the last linear layer will project everything as it wants, right? So basically, that's why we add these non-linearities in between, and you can think of this as like, you have this space of data points, and we kind of like pull them out and then cut them, pull them out, cut them, and things like that. So, but now regarding the car brands, so we have this this non-linearity here, and let's see that. Imagine that index 0, right? We have these indexes. So let me illustrate. So index 0 means Mercedes, right? Hopefully I wrote it correctly, probably not, right?
It's only one S.
Yeah. So then 1 BMW, 2 Opel, all of the German cars, right? So where is so I don't know, like Chevy and so on. And then so for example, TTT, 10 is Lada, right? And now what happens is that if I store all of these values as indexes and give them to the network, so if I give them, for example, BMW, I will get very low output. If I give the Lada, it will get very high output. So it doesn't make sense that basically just because I changed the indexes, now I put the Lada first or Mercedes last, that I get very different, huge output difference. So yeah.
But does it matter if the model sees all the training data?
Yeah, like technically you can train it, but now let's keep listening and trying to find reason why this is not good. Okay, technically you can train it, but keep looking at it. So the difference, let's now think about the difference. So BMW and Opel, right? So here the difference is 1, right? And difference between the BMW and Lada is 9. So it's the distance between those values very large distances, right? Plus also the thing is that it depends on the indexes. If I add something first or last, it changes completely the data structure landscape. So it's not that the model cannot learn it. The problem is that when we start learning it, right, it kind of gives this prior knowledge that it says that Lada is 10 times better than BMW or something like that. So it's about the prior knowledge, about the prior locations of the data. Do you get it? Like the model can learn using this. If I train model with this, at the end it will kind of work, but it is totally not the best option to start training with this kind of layout. Do you understand? Like I will give examples more.
Yeah, but I'm not getting why the model interprets it as if the Lada is 10 times more worth than the BMW.
Yeah, no, it's not. It's just a way to explain. Of course, it does not think that this is 10 times worth. It's just that for the hidden layers, it will get values with a larger magnitude. And this magnitude is defined by you as a data engineer, right?
So the layer depends on what it has seen before.
Yeah, that is again a little bit different topic. So we are talking now about data pre-processing.
Yeah.
I want to pre-process data in a way that I don't bias my model initially to give assumption that there is bigger difference between two data points. So if I have as an input kilometers driven, right?
Yeah.
If the car is driven a lot of kilometers or a little kilometers, they're like logical path, like I'm going more. There is no logical path just because I ordered that Lada is first and BMW is last, you know? I can swap all of this around, it will be completely different logic there. So it's just, it can work, but it's totally not optimal. And one way to talk about this is that the distances between all of these guys are not optimal. So the correct way to do this is a little bit different. So the one easiest way would be just to encode all of these guys as the probabilities or the one-hot encoded vectors. So let's say, and I will explain just in a second. So we have the first, so this is Mercedes, comma, chick, onto and then 0. Then we will have for BMW this kind of vector. Then we will have for Opel this kind of vector, and so on. You get the idea, right? So and for next one a little bit longer. So unfortunately you have here, so this will be that. And as you see already that, let me add here the same format for all of them, that the magnitude of each of these vectors are the same, right? So we are not biasing, we are not making that initially before model starts learning, we are not pushing the model towards some part of these non-linearities. You're not saying that just because you accidentally given this magnitude, we get some value up here or down here. All of these values initially will fall to the same magnitude. And then later we learn to use each dimension separately. So basically it will start encoding some stuff from the BMW, from the Mercedes, and it will not be all just mangled because of the indexes. So that's one way.
So try to get a data set that is as balanced as somehow possible.
Yeah, doing the data pre-processing,
yeah,
to make sure that model has no bias towards any particular brand, or like automatic transmission, manual transmission. They both vectors pointing maybe in separate directions.
But I mean, in the end, you will never have perfect balance in the data set, so.
Yeah, so let's keep looking at that. So then, what to do even better is just assign for each of these elements not just one hot encoded vector like that, but just assign the learnable vector. So this would be, let's say, the some kind of VA1 W. So I will not write everything because it will be too long, but basically, we can create this kind of matrices, and for each of these vectors, we will have initially. I will explain just a second. BW. So not A, but B. Sorry, B, B2, B. You get the idea. So that we create learnable parameters in vectors for each of these elements. And basically what it means is that what we can do is either initially set all of this random, so that all of them are approximately at the same magnitudes, approximately at the same place, at the same time a little bit off, right? Or we can set everything to 0 as well. Then we say all of the brands are equal and start learning. And when they start learning, what will happen is that they will start clustering. They will say that high-end brands cluster here, low-end brands cluster here. So it's basically, it will try to optimize the space to use the data more efficiently. So it will not be, so here you see three ways to encode data originally. So this is the kind of prior knowledge of using just the scalar value, which is have a lot of disadvantages. Here you say everything is equal, right? Your prior knowledge, and here you say decide yourself which one is more closer to each other. So and in order to do this, so to think about it, it's basically we could if you have this huge matrix, we can just do the dot product or multiply this guy with this one and select out that row. or we can just programmatically select that we have this huge learnable matrix and this row corresponds to that card, this row to that card, and so on. Is that kind of clear, right? So we're trying to pre-process data so that it is as neutral as possible and at the same time like gives the information necessary. So here the only prior at the end is we select which column, which row we use. So that is our kind of input prior here. But if something is not clear, then need specific question, okay? We'll implement it and hopefully it will makes more sense in code as well, okay?
But what is normally the most neutral way to encode?
Yeah, this one. It's like sometimes if you definitely know that all of your inputs are equal, you know, I don't know, like your robot goes in 4 directions and basically there is no like specific more obstacles on left side and right side, and maybe let's encode that, it doesn't matter. But if there is like, I don't know, if this car is better than that one brand, maybe I should give the model opportunity to learn this. So, but again, yeah, so the main thing is anytime you see anything that is categorical, never use just index. Basically, that is the kind of the most difficult way for model to learn. So then, okay, let's back up to the code. Let's do that a little bit, and then we will take a break. So code, it will not be difficult to add. So that's why I added here +4. And I'm multiplying that by embedding size here. Embedding size means the number of dimensions per each class which I want to learn. So and it's a term. So there's a lot of cool research regarding embeddings. You can kind of encode all sorts of things into embeddings. Like if you have a large image, you encode it just in 100 dimensions, and then you can get similarity. Is this image similar to that one? And like language models, there's really a lot of things that you can do with embeddings. Okay, so that is good. Then the next thing is let's create these matrices. So matrices we'll call M's, and this will be torch. And then module list, we are using module list, not simple list of Python, because we want model to understand that they have learnable parameters there. I can use also simple list, but then the model will not find that there is a parameters. So in the Python, by the way, the variables which you don't use, you usually write with underscore. I can write also E here, but basically if I don't use it, I can call it as that as well. So that's kind of one way how people usually do. Ah, no, but actually we need that. So we need I. Sorry, we need I. So then self emps append. So torch and embedding. We already have this matrix. By the way, we could use also linear and then apply the dot product. But if we already have that kind of function, let's use a function we already have in PyTorch available. So the embedding function, right? So here the embedding dimensions, embedding size, and then number of embeddings. How many brands of cars we have? We can get this information from dataset. Dataset full labels. These are categorical labels. So these are categorical labels like car, brand, and so on. So we get those embeddings from there. Yeah, I mean the number of embeddings, the rows, how many rows we want. So that's about it here. Now we only need to add this stuff to the forward pass, and that's it. So now let's wait a little bit with this one and then move on to the next step.
Are you sure that those dimensions are working?
Oh, dimensions. I'm not yet finished. So.
Yeah.
But I hope we'll see.
But you now added all kind of things, so fuel, transmission, and seller type to be this.
Yes, so see, it's already split here. X and X classes, they already split. So X contains the not categorical, X classes contains only categorical stuff.
Yeah, I mean the EMDS is now. So those for the fuel.
Yeah, yeah, I'm adding the elements here.
Okay, yeah.
And then I will be using them. So now on the other end, what we do is we will call here m's. So this will be initially just a list here, and then we add slowly stuff to that list. So again, add the same table for I in range of 4, because we have four types of categorical inputs. And to do this, then we have xm's append the output of, maybe be nice to have not macaroni script but in 2 parts. So xm will be the self m's I forward x classes, all rows which are batches, and only the column which I need, like that. So this is good. xm is added. Now I have these guys ready. Now what I want to do is concatenate them together as a torch vector, torch matrix, basically. Torch m's, torch cat, concatenating these lists xm's by dimension of -1. So I want to leave batch comma embedding size.
What is cat?
Sorry?
What is cat?
Concatenate. So like if I have 2 arrays, I want to put them together. So and this is very specific. I'm not just putting all in the long sausage. I'm putting them in a specific shape. So I'm adding that this will be batch comma embedding size times 4. And before that, each of these guys was just like that. And then all of these were basically before this one. It looked something like something like this, 4 comma that, but not really, because that was a list. So it was in a separate list here, and then I created in that way. In that way, I created this stuff. I hope that I did not mix them up. Let me see. Okay, maybe not use concat. So this is a little bit tricky because it might screw up the way how it's defined. So let's see, stack. We could use the stack probably. Let me see, concat. I think it will work like that as well. Okay, I will add the breakpoint and see you later. So that is that. Then also the x, so tx combined is again torch cut x and tx embeddings with dimension of -1. So I'm just concatenating, adding to the vector of the numerical inputs, categorical inputs, which are now encoded as these learnable embeddings. So now I just double check if it works, and then I will share it on the Jamboard as well. Yeah, it works. We'll also need to, in the break, I will check that the equations are correct, but I think they are. So adding this to the Jamboard, and now it works. So yeah, so the idea is that I converted these categorical indexes to these vectors, added all these vectors together in these batch comma sausages, and then added the actual axis, and then passed to the model. And this works only because I added also here in the model itself 2 + 4 times embedding size. If this input feature would not match the result which coming in here, nothing will work. So basically, they definitely must match. So the size of this guy must match the size which we defined there. Okay, so now we are good at regression models, basically. So you can start predicting your car prices and all sorts of interesting stuff. But in the next session after the launch, we will do the classification. So this is like trying to predict if what kind of car brand is it actually from the other inputs, or is it automatic, manual, and things like that. And that will be useful also later to predict in CAPTCHA, is this letter A or B, or something like that. So we don't predict the letter A just by predicting the number of the ASCII code, Okay, so far so good. I will put this all on break and